If you run poc.2.py now, it will try to log in, and then it will send the username and then 5000 A's as the password. Hello and welcome to Crazy Danish Hacker. Today you are going to learn how to write an exploit for a stack-based overflow. Here I have a Windows 7 virtual machine and also a couple of files that I have copied to the VM. I've also changed the background image, but I haven't changed anything else. First we will need to install a debugger. And this is straightforward. Once we have installed our debugger, we will need to install the latest version of Python to ensure that Mona will function as intended. When you install Python, make sure that you do not change the default directory. Next, we will need to install the Mona plugin for the debugger, so we will extract it. And then we will copy the mona.py file into the directory. C, program files, Immunity Inc., debugger, and py commands. Next, we should install a text editor. This is optional, but it does help understand the Python script that we are going to write. In this case, I have chosen Sublime Text and a portable version, so we don't need to install it. Before we continue, we may need to add a network device to the virtual machine. To do so, open the settings. You can do so by pressing Ctrl D, and then we will need to add a new Ethernet interface by selecting Network Adapter and clicking Finish, selecting NAT, and then OK. When it has finished installing, you will see a pop-up in the lower right, and you can select Home or Work Network. Now we are ready to install the vulnerable service. In this case, it's a mail server called SLMail. The installation of this software is almost straightforward, but there are a few things to keep in mind. Make sure that you bind to all IP addresses, and make sure you change the domain name. In this case, I've changed it to cdh.local, and I've also changed the DNS. You should not change the other settings, as that may change the exploitability of this service. Once we are done, we should restart our computer to ensure that all the settings from SLMail have successfully been installed. This whole process should only take about 5 to maximum 10 minutes. You can get all the files needed for this YouTube tutorial in the description below. Alright, now we are almost ready to begin. You should also have a Kali Linux virtual machine running as a separate virtual machine. In this case, I will switch to it now. And you can see that we have the most recent version of Kali. This is mainly so we can run MSF Venom to generate our shellcode later on. In case you want to change to Undercover mode, go to the menu and write Undercover and then select Kali Undercover mode. You will also need a console on this machine, so you may as well open it right away. To make things easier, we will create a new folder called exploits, and this is where we will do our work in. First, let's open our text editor again and have a look at the original exploit. This will be our basis, and this is what we will recreate from scratch. Let's copy our sample exploit into the exploit folder and then rename it to POC. This means proof of concept. The original exploit was found by Mutz from Offensive Security, which is also the company behind Kali Linux, Backtrack, and of course the various online courses that they offer. If we run this exploit unmodified against our current virtual machine, the exploit will fail as the return address and also the shellcode may not be compatible. In this case, this return address may not work, and this IP address will also not be the correct one either. Let's open our POC and create a new template. The template that I'm creating here will also be available in the link below. In case your computer starts to respond very slowly, consider turning off Windows updates. This is only necessary in case one of the Windows services is using a lot of CPU and you have a hard time using these small programs. Alright, so here is the basic template that I've created for this exploit. Here we will define new sockets. This is our buffer of 5000 A's. Here we connect to localhost on port 110. Then we receive the first 1024 bytes and print it to the screen. Then we try to log in with username and print the data that was received. And finally, we try to send a password with the buffer, which is 5000 A's. And if we get a response, we will read it and then print it to the screen. And last but not least, close the socket. Let's save a new file so we can use this later on in case we want to go back. Before we continue, let's make sure that SLMail is running on port 110. Here is the program identifier. And as you can see, program identifier 1900 is slmail.exe. To make it easier for ourselves, run services.msc and go down to Seattle Lab POP3 server and make sure it's started. Keep this window open in case you need to restart the server. You can do so by starting and stopping it here. It's also valuable to have the task manager open sometimes, because you may need to forcefully crash the SLMail process here as well. For now, I will minimize the windows and open our debugger. It's very important that we run it as administrator, because we will otherwise not be able to attach to our process. Before we continue, we may need to change the font size so it's easier to see what's going on. In this case, we go to Options, Appearance, Fonts, Change. In this case, I prefer using Lucida Unicode in this case. Click Change, and I will select font size 12. Then right-click, Appearance, Font All, Lucida Unicode. Let's try and attach to our process, and then continue. Make sure you have selected SLMail and click Attach. If the text is still very small, try and right-click again, select Appearance, Font, and then Lucida. Now it's a lot easier to see, especially when you're watching this YouTube video. Right now, the program has been paused, as you can see in the lower right. You need to run it again. You can do so by going to the debug menu and selecting run, or pressing F9. Now the process should be working, so we can actually try and run our first proof of concept, which is poc2.py. Open a new command prompt, and then cd, right click, paste, and then enter. You can get this string by clicking up here and copying it. We don't need to use poc.py for now, so I will create a new folder and move it away, so we don't accidentally run the wrong file. If you run poc.2.py now, it will try to log in, and then it will send the username and then 5000 A's as the password. As you can see, the service crashed as it says access violation when trying to execute 41414141. So basically we overwrote the extended instruction pointer, which is pointing to where in memory that the program should execute the next instruction. We will get back to that later in the video when we execute our shellcode. In short, if we can control EIP, there is a good chance that we can execute our own code by injecting our own shellcode into memory, in this case onto the stack, which is down here, and then we can run anything that we want to. It's also useful to change this view to 16 bytes as well. So right click, hex, and then 16 bytes. Now there are two ways to continue from here, as we want to run the exploit again, but with different settings. We can pass the exception to the program by holding shift and then pressing F9. This will allow us to continue to run the exploit again, but without having to restart the program or restarting the debugger. Don't worry too much in case this is blank or this is blank. This is fine. Just make sure that you see something after you run your exploit. From here we want to find out where we overwrote EIP, so we will create a special pattern and replace the buffer variable with the pattern. We will create the pattern with Mona. In this case I will just change it to Unicode. We will want to use the command known as pattern create. So in this case, we are creating a cyclic pattern of a given size. In this case, we want to create a pattern of 5000 bytes. It's very important that you do not copy this string from here, as that will not be the full string. Instead, we need to go into C, Program, Immunity Debugger, and Pattern. So copy this, make sure you get all of it, and then go into your Sublime text editor. You can also use Notepad, but you won't have this fancy highlighting though. Comment out the buffer variable, create a new variable called buffer, and then paste in the cyclic pattern. Now we can rerun our exploits and find out where we overwrote EIP. When you're in this mode, which is L for log output, but also for Mona, you can also press C to go back. So to switch between Mona and the normal view, L for Mona and C for CPU view. So let's try and run our updated exploit. Make sure that you have saved it. So save and run it. If everything goes well, you will see something like this, and this is what we need. So copy this. Then in Mona, we will use pattern offset and then paste it in as follows. Press enter and scroll down, and you will see that the position where we overrode EIP was 4654. So if we go back to our exploit, we can delete our cyclic pattern or comment it out in case you want to keep it for memory. And then we will reuse our existing buffer and then change it a bit. So 4650 plus EIP plus nope plus shellcode. And then we have to define these variables above. So EIP will be 42, for example. And since we are exploiting a 32-bit process or program, the EIP will need to be 4 bytes long, as that is equal to 32 bits. For the nopes, you can use x90 and then 16 of them. I will get into what this does later on as well. In some cases, you may not need nopes at all, but it is useful to know what they do and also how they help make your exploit more reliable. For the shellcode, we will use xcc and write 300 of them. This type of bytes in machine code is equal to interrupt 3. More on that later on. Good. So here we have our buffer that we will send. So now let's try and rerun our exploit. Go back to CPU mode by pressing C or pressing Alt.C. Then press Shift F9 to restart or pass the exception. And that way we can rerun our exploit again. And then run it. If everything went well, EIP will now be 42. You will see some nopes here on the stack, and you will see the rest of our shellcode. So if we follow the ESP in dump, you can also see our injection here. In case this goes blank or missing, try and click this up here. All right. So you can see here is some of our injection. And then we have EIP, our nopes, which are non-printable characters, so that's why it's blank, and our shellcode. Now, since the stack is executable in this case, we can jump to the stack here, and then we can jump to where the ESP is pointing to. In this case, ESP is pointing to this memory address. Let's follow on stack as well. So if we change EIP to this memory address, then we would execute these instructions. And then we would stop here after executing the first one, as that's an interrupt. So that functions as a breakpoint. We can't just change EIP to this memory address, as this may change from system to system. Instead, we need to find something that doesn't change at all. And the easiest way to do this is to find an opcode in memory. Now to do this, we should check out the modules loaded by the SLMail program. In this case, we want to look at this, and also some of these. That's because ASLR is false on these, and save SH is also disabled, and NX combat. These flags make it more insecure, but easier for us to exploit. The easiest way to usually do this in Mona is to use the jump function. In this case, you can run jump -r ESP and it will search all executable modules and see if it can find something that you can use. This may take a bit, as it's going to search all of the DLLs and then try and find what you need. You may need to switch back to the mono output mode or log output by pressing Alt+L or clicking the L button. In this case, it says it has found a total of 0 pointers, but that does not mean that we cannot find any. Now, to jump to ESP, there are several ways to do so. One of them is to execute a command known as jump ESP. So if you write ASM space and then -s space jump ESP, go back to log output mode, which is also where mono is, then we will see that the full opcode is the \x ff and then \x e4, or in short, FFE4. So that's hexadecimal. So what we can do is that we can use mona find. So let's say help find, and make sure you memorize this or write it down. In this case, we can put it in a comment, for example, and maybe even copy it as well, as we will need to use it shortly. Now, the other function called jump basically used a different way of using find. Now, the jump function is more like a simplified version of find, or a different implementation of find. So we will try and find our opcode ourselves by using find. We don't want to search all of the memory. We only want to search DLLs such as the ones that have false flags like OpenC32, SLMail, SLMFC.dll, exception handler.dll. In this case, I recommend you use this DLL, so SLMFC.dll. So if you write find mslmfc.dll, and then you need to type in the pattern, in this case FFE4. So the whole command to search slmfc.dll for jump ESP, in this case FFE4, is as follows. Let's try and execute it and see what happens. As you can see, several results were returned. In this case, we will copy the first line and copy it to the clipboard. We only need the memory address, so we can take this, for example, or we can delete this and keep a comment about it for later use. Next, we will need to take this, and in EIP, we should add some spaces to make it easier for us. Now, there are other ways to do this, but this is the manual way, which is easier to explain as well. Now, when we send this string is actually reversed. So in order to go to this memory address in EIP, we need to type it in as follows. So we won't type in 5F4A35 8F. Instead, we will type in 8F 35 4A 5F. And this will actually become EIP, like this. So now we can try and run our exploit again. So we go back to CPU view, Shift F9. Make sure that you have saved your exploit and run it again. Now, in this case, it will look different, but in this case, we are correct. Now, the way that you can find out you are correct is in case you see CC int 3. And if you scroll up, you will see our nopes here. So that's the no operator instruction. And before we have our EIP injection, which is here, including 2 nopes. And then we have our A's.